Hello, hello, hello. Welcome to the Julia Dispatch. I'm Chris Rakakis.
And I am Michael Thiemann. And today we have a very wonderful guest with us. We have Guillaume Dalle. Did I
Nope, not even
pronounce?
close.
Guillaume Dalle. We just talked about
We went over this.
Wait, what did I do?
It's the family name you got wrong. It's Guillaume Dalle.
Dalle. Oh, yeah, sorry.
All right, we're not editing that out. There's some public shaming there that is required. But all right, so so today, and we'll be chatting all about, if people are interested in topics like automatic differentiation. Well, here's the episode for that. So I guess that first of all, it would be great for you to introduce like how do you want people to think about you? Give a quick introduction.
Ideally, I want people to think about me as someone nice who helped them out with their Julia stuff. So I guess most beginners come across me maybe on the Julia discourse, maybe on GitHub. And so really what I care about most is making people's code go brrr. That's sort of the main goal here.
That sounds lovely.
And the alternative version of that introduction is so you were a postdoctoral researcher in machine learning at EPFL. I guess you'll have something to say, but
Yeah, still am until next month.
Okay.
Yeah,
and then what will you have?
I'm joining a laboratory at École des Ponts in France as a permanent researcher. I'll be focusing on applied mathematics for transportation systems. So hopefully there's going to be a lot of optimization there, maybe some machine learning, industrial applications with what I wish will be sizable concrete effects on CO2 reductions and a lot of Julia code as well.
And I assume you'll be looking for students as well?
Yes, definitely. I'll be hiring lots of master students, PhD students, postdocs. So if anyone from the Julia community is hearing this, watch out for, job postings on the Julia discourse and on my webpage.
Cool. We already jumped very much to the future with you setting up new positions. Let's get back to the origin story real quick before we go there, and we'll get there. So you started to commit to Julia and to commit to the community around your PhD. So give me a little bit more of the origin story, if you will. Like, have you been coding already during your studies? What technology have you been using before you committed to Julia?
Yeah, so definitely I did a lot of coding during my studies, mostly in the language that starts with P, but in other languages as well, even more cursed, Java, C++, even OCaml.
I've used a lot of Perl too, so.
Yeah, so we're all guilty of something, right? But in none of these languages did I feel like I could contribute anything meaningful. Precisely because to be efficient, for instance, in Python, you would have to know a lot of C or C++ to write the low-level libraries. And so I was a programming language user back then. And I guess sometime during my master's, one of my professors suggested that we do a project in Julia, or one of my classmates suggested that we do it in Julia. And it just stuck with me how fast we could be with barely any effort at all. So I kind of got roped into the language also because it was so pleasant to write. I found it very elegant, and the style of code that I was able to produce was aesthetically much more pleasing than what I got with Python. And so I gradually used it more and more until one day, I think it was my friend Mathieu who tricked me into becoming a maintainer of Julia graphs. And it all went south from there, really, because you start, opening some minor issue on a package, and the next thing you know, you're maintaining half a dozen ones which are core parts of the ecosystem, and you're overwhelmed with pull requests and angry users, and that's what I love about it.
Yeah, we've really pulled you into the maintainer space. Awesome.
Yay!
Does this mean you tell people be careful how much you want to get involved, or is this something that you would recommend, even though now you know that it's easy to get like immersed into this important role?
Oh no, I'm definitely telling people go have fun with it. I watched the episode with Tim Holey, and from what I gather, he was trying to do neuroscience, and he basically was sidetracked into refashioning half of the Julia ecosystem in his image, pun
Mhm.
intended.
Yeah.
So I don't know. I think it's easy to get overwhelmed, but at the same time, it's very empowering to see that starting from a beginner level, you can actually have meaningful impact on the ecosystem. Last year I took on a couple of interns, bachelor students, and
Mhm.
they started from scratch in Julia. They didn't know anything about the language, and in 6 months they were writing code that was state of the art for parallel graph algorithms, for instance. So
Yeah.
I think that's really a strong asset of the language, that you can go from beginner to user to contributor to overwhelmed maintainer in a matter of months.
Yeah, that's
Mhm.
really cool.
And I think it really changes the research trajectory too, right? I mean, because a lot of times people who are doing research, especially in the computational space, they're trying to come up with like, oh, this would probably be a very useful thing. And then when we actually start to work on the open source software, the software people use, you kind of realize like, yeah, these algorithms wouldn't have an impact because X, Y, Z or whatnot. But if you're actually working on the software that everyone is using out there already, if there's 10,000 people already using the software and you make it 2 times faster, then you know that that's state of art the art for them, and it's really making a big impact, right? And there's just, but then you also have like 100 issues that you have people pinging you about every day of like, oh, what would be making it better? This, and this. And so suddenly your research, you no longer have in this thing where you don't know what to work on, right? I bet you know exactly what you need to work on the moment that you close this tab. You have a lot of people asking you for it, and that's a very interesting research environment, right?
Yeah, and it's many people don't actually consider it research. Like I've had disagreements over this, because indeed, the moment I started contributing more strongly to Julia, I shifted my some of my research interests towards a more practical software engineering point of view, and many people think it's worthless research, but I actually think it's a vital part of the research ecosystem, because good software breeds good research projects, and you can't do one without the other. So
No. I I would be with you on this one. The reproducibility, in particular, if you have a very solid foundation, goes a long way with being able. Okay, I can clearly see what you did. I um, can rigorously check everything that you like. It's in thinking this to the logical conclusion, you almost wouldn't even need to write a paper anymore if the code would generate your figures just from if you import and say paper Guillaume, and then it
got the name
produces the
right.
figures, and then I'll learn. Then the argument is so compelling, and then people can build upon this. It's really
Exactly, but
important. Yeah.
there's already some journals and publication venues that take this to the logical conclusion. Like Journal of Open Source Software is a venue where you
Mm-hmm.
actually submit a repository and not just a paper. And there's this new journal I've heard of in France called Computo, which is built upon Quarto. And so here you don't submit a LaTeX paper, you actually submit a Quarto notebook with reproducible experiments built into the very fabric of your paper, which is, I think, really neat.
Mm-hmm. Cool. So before we dive deeper and more deep into the technology, and in particular, the one thing that I want to talk about most is the differentiation interface JL package. One more thing that really struck me when I did the background research is how much of a humanities background you have, right? So you really took courses during your studies that is outside of the pure technological space. You on your website, you're listing all these resources for other people. You also helped setting up the Modern Julia workflow website. So, um, tell me a little bit more about this very people-oriented way of approaching technology in your work.
Well, it's not just technology. I guess it's more broadly. I really like teaching in particular,
Mm-hmm.
and that started very early on. Like 5 or 6 years old, I wanted to be a teacher, and every time I would go up one grade, I would want to be a teacher of that exact same grade because I was having fun at school. Yes, I was a nerd early on. So are you probably. So yeah, I've liked teaching for a very long time, and I like the way my thesis advisor Axel Parmentier framed it when he said, okay, like writing research papers is cool, but the real societal impact we have is teaching students. And so I take this job really very dearly, and I try to provide the best resources and make it fun and accessible and engaging. And as far as the social aspect goes, it's a peculiarity of my engineering school, the one I went to in France, because they had us take humanities classes precisely so we wouldn't become entitled Silicon Valley jerks. And after that, I think the COVID crisis in particular really highlighted for me the need for more platforms and more resources, especially for PhD students. I remember that time was a very lonely time, and for me trying, I had lots of mental health issues, and I really found comfort in this Discord platform server that friends set up to gather PhD students from all over France, because we were all working from home, struggling with our research, with motivation. And there was this wonderful Discord where we could just go to and chat about our issues and exchange research ideas, or just hang out playing Among Us, and also discuss about struggles. And I realized that PhD students are often left to their own devices, and that's why I started building this website called PhD Resources, where I point them to tools for their research and also tools for their health to make the journey a little bit easier. So it's always been rather important to me, but I think the COVID pandemic really shone a new light on how much we need to be in a group and be supported, and not just be lonely scientists in front of our desktop.
Yeah, I absolutely agree. The pandemic. So we are recording this at the end of 2024. The pandemic is like only 2 years away.
Yeah, and some people are still catching COVID, dying from COVID.
Yeah. And it's sometimes it's completely mind blowing how forgetful we are already as a society with the immensity of what just happened. But I also like how you or let me phrase this as a question. So my experience of the Julia community was very open, very welcoming, very supportive of each other. And do you think that this also played a role for you in these years where okay, we all lived through very difficult times, but finding this community where, as you said, the you can go from beginner to being deeply immersed into the core development team, or like development teams across different ecosystems and work packages. Like, was this something that contributed to your, well, let's say, passion for this particular technology?
Oh, definitely. So during my PhD, this Discord server I told you about was one of my communities, the one I felt I belonged to. And gradually I felt like I belonged more and more to the Julia community, which I really enjoyed in particular because there's a ton of really smart, really talented people, and they don't look down on you. When you ask a question on the Julieta's forum, usually you get some of the smartest people in the community to just answer right away without a hint of judgment or criticism or anything, just telling you, okay, this is your code, it's great that you got here, now let me tell you how to fix it. And I love the fact that we could be so close to people who actually created the language, even, or people who made foundational contributions. And yeah, it just struck me as something that I want to be part of, that I want to belong to. And I feel like it's also shaping my research career, because it's giving rise to lots of different collaborations with people I, for the most part, have never even met in person, except maybe at JuliaCon. But you meet on GitHub, and then you talk, and then you build up research projects from scratch, because this is a community where people respect each other. And also it's just plain fun. Like I love seeing every time. The best part to me is whenever someone posts something on the forum to the tune of Julia is 20 times slower than MATLAB. this is like the surefire way to get maximum engagement from the community. But no one is looking down on you. They're just piling up to make your code 1,000 times faster. And I really enjoy seeing this because yeah, it's fun and it's interesting and it's educational and it makes you feel like you're part of something bigger.
It's very easy to nerd snipe people from the community.
Yeah.
Oh, I
In that
mean, like
particular
the
way.
community is almost designed for nerd sniping. Yeah,
Yeah.
just just post something that just says performance issue, and it's like, oh, everyone just like drop their research, and they'll be like, "There's a problem on the internet."
Yeah, that's true. So let's now shift to really the technical nitty gritty. What are we doing with Julia here? So the reason, as I already hinted at, was your package differentiation interface.jl got a lot of traction, and it's at a time of preparing the episode, it was only 9 months old, but still, I think from judging from the buzz that I see around it online, it might be the most common AD package right now. So why did you start it? What was the origin story of that particular project?
So actually, I think it's intertwined with the origin story of modern Julia workflows, which is the other big thing I did in the Julia community last year. So it started from a video by Martin Smith, which was a tutorial on some aspects of Julia development workflow. And then we somehow got in touch because we wanted to write this down because I didn't like video. I want to read stuff on a web page without, people talking to me. And so I connected with Martin and we started on this project, Modularity or Modern Julia Workflows, which was initially not named that way. It didn't really have a name. But the idea was to sort of take the beginner Julia developer who has an idea about syntax, like how to write a function, how to write a for loop, but doesn't really know how to set up their environment. Maybe they're just restarting their REPL from scratch every time they run a file. Maybe they don't know how to add dependencies and everything ends up in the main environment. So all of these, tiny little tricks that seem maybe obvious to more experienced developers, but that make life very difficult for newcomers, we wanted to put them all in the same place. And we realized that it would be very time consuming and probably frustrating and doomed to fail if we tried to add all of this to the documentation, because it means opening 1,000 PRs and waiting sometimes months maybe for review. So we decided for a quick and dirty solution, which was to set up a blog with Franklin, and we started it. And we reached out also to Adrian Hill, which was the third member of our group, because he had a lovely course on Julia for machine learning from which we wanted to borrow content. So we ended up chatting. And at one point, I think the conversation shifts to automatic differentiation, because it's another area where things are a lot more complicated than they should be, right? Where there's a lot of options, like for development workflows, it's not easy to pick the best way to do things. And there's 1,000 different people with various opinions telling you what to do. And there was an existing project called abstractdifferentiation.jl, which we thought had all the right ideas in terms of making it easier to access different automatic differentiation libraries. In Python, you have three main autodiff libraries. You have PyTorch, TensorFlow, and JAX. And you write your code in one, you pick one of them, and then you write all of your code in it, right? And once you've done that, you're sort of condemned to stick to the same autodiff framework that you chose from the beginning. And in Julia, it's a bit different. You write the code first, and then you try to differentiate it with one or two or more autodiff backends, and sometimes it works, sometimes it fails. And abstract differentiation allowed you to abstract all of this away by saying, okay, I don't actually care what is doing the gradient as long as I get a gradient. Because while autodiff backends may come and go, the notion of a gradient or a derivative or a Jacobian will stay. So it hit all the right notes, and at the same time, it didn't get wide adoption in the ecosystem. We thought mostly because of performance issues. And so initially, we set out to write something called abstract diff next, which would eventually be merged into that package. But we sort of got sidetracked and very, very heavily nerd sniped with Adrian. And this turned into a full-fledged library with, I counted this morning, it has 14,000 lines of code. And it's very different than abstract differentiation, but at the same time, it does what abstract diff wanted to do, just in a slightly, I don't want to say smarter, but we learned from the design that they proposed, and we suggested one that would be perhaps more likely to be adopted by the community.
Yeah, I mean, when we first started abstract differentiation, right? The thing was like, let's get something together that will be a starting point, right? And then we'll keep on growing, and we'll have to add a bunch of things. But it turns out that, yeah, I mean, if you want people to adopt automatic differentiation, it's probably very performance focused, and so you need to make sure you handle caching, you need to make sure that you handle sparsity, and you need to handle all those things, or else people will just use the library that is a bit more efficient, right? So yeah, I think that the differentiation interface stuff. Once you started really digging into it, I think you asked me, you're just like, because yeah, I was part of the development process in abstract differentiation, and then I had like libraries using 5 differentiation libraries at the same time instead of using that. You're like, why the heck are you doing that? And you're like, it never got fast enough. So then you're like, okay, I want to solve that issue. I'm like, great, we finally roped someone into this mess. Go have fun. Here's what we need to make sure that you solve. And I think that you've made a lot of inroads into a lot of that, right? Especially with like common caching interfaces and common handling of sparsity. I mean, how you want to go into a bit of a detail there on any of those bits?
I think the key design difference which enabled really all of this is the concept of preparation.
Mm-hmm.
Because usually when you compute a derivative or a gradient of a function, it's because you're using it in some form of iterative procedure. Maybe a differential equation solver, maybe an optimization algorithm. And so you're actually not just going to call one gradient. You're going to call it 1,000 times, maybe 1,000,000 times with the same function and with an input that's roughly the same type and the same size. And what that means is that you can actually prepare ahead of time. You can say, okay, I'm willing to spend a little bit of time before my iterative procedure to set up all the right memory structures, to pre-allocate everything I can, maybe to detect sparsity patterns and exploit them to make things faster. I'm willing to spend a bit of time at first so that every single call to my gradient or to my Jacobian or to my Hessian is much faster. And that was the key design difference from abstract differentiation, is that we allow this two-step mechanism where first you prepare for the thing that you want to do and you spend a bit of time, but then you do the thing you actually want and it goes boom.
Yeah, and I think that there's a lot of advantages in having that be in a high level interface because, yeah, like in a very specific, if you're just talking about forward mode automatic differentiation, like forward diff, right? Forward diff only knows the world of forward diff. So it does have a preparation mechanism, right? It has the Jacobian caches, right? But its preparation mechanism is only about forward diff. So it doesn't know things like sparsity detection or whatnot. And so it's just like, it's always you need to have multiple tools together in order to really do the preparation that and make use of all the best parts of the ecosystem in that phase, right? And then you build screaming fast code that you can call over and over. So I think it's been evolving very well.
Yeah, and
So
it's also the goal was to save a lot of work to a lot of people because, as you said, the current state of the ecosystem was there's maybe 5 popular autodiff frameworks. Like among the most popular, I would say forward diff, zygote, enzyme, and then maybe reverse diff, finite diff, something like that. And so every single meaningful Julia package has at least 5 extensions that re-implement the gradient by binding it to every individual library. And this makes no sense because it's better to centralize these bindings. Most of the needs of all of these libraries are similar. So we might as well just put that code, which is duplicated all across the ecosystem, we might as well put it in one place, maintain it, optimize it, test it to the bone, and that way everyone benefits from it. And you're right. Once we have a common interface to calling different auditive backends, we can actually do more with it. We can do second order operations where we mix different backends, which is of course not possible in any individual package. Or we can do sparse operations by leveraging something external like sparsity pattern detection and coloring, which we also implemented with Adrian and Alexi. So
so
it's really about making life easier for people, and so that they don't have to read the documentation of every package.
it definitely makes life easier because I literally have a colleague who decided not to continue using Julia because he was overwhelmed by the choices of AD backends, and he was like, okay, I don't know what is best practices here, so let me go back to Python. And yeah, that was a sad story, fortunately. And now I might be able to tell him out. Now I have a definite answer for you. The thing that strikes me in this part of the conversation is that, so in previous conversations, one recurring theme has always been being so close to the compiler and to the core language features enables a lot of things. And what differentiation interface.jl is reminding me of is something like a intermediate language between a front end, which is the code that you write for like your forward pass or the forward pass evaluation that you want to do, and then the AD part, the gradient part, seems to be like a compiled backend, if you will. Like, is that something, or tell me a little bit more about how the matching between, okay, I can do whatever I want into what code I want to take the gradient of, and here I'll be able to match it to these different interface libraries for taking the AD framework.
So initially, we actually wanted differentiation interface to be absolutely an empty package. We thought it should just define functions, gradient, Jacobian, but all the code should actually live in package extensions. That was our initial design with Adrian. And we quickly realized this wouldn't work because every auditive backend implements a different subset of the operators that we need, or the functionalities that we need. Like some don't implement the Jacobian or gradient, some don't support maybe scalar inputs or vector outputs. And so we had to make some opinionated default choices as a way to enlarge the functionality of every backend to support the bare minimum, if you want. And the bare minimum is scalar or vector input, scalar or vector output for derivatives, gradients, Jacobians. That's like the bare minimum that we wanted every backend to be able to do. And to do that, we had to define some default operators. So what happens when you call something in differentiation interface is that it essentially checks if the operator is available with a specialized implementation in the specific backend that you're calling. And if not, it goes through a series of fallbacks to implement the complex operator based on more simple operators. And that's the gist of automatic differentiation. It's very close to the actual theory of it, which is that everything you want to do, you can do with two fundamental operators, which are the push forward and the pullback. They're also called JVP and VJP. And if you want to know more, you can watch our JuliaCon talk 2024 on gradients for everyone. But essentially, that's what it does, is explain how you go from push forwards and pullbacks to more sophisticated operators. And differentiation interface goes the other way around. And it breaks down the sophisticated operators, if they don't exist in the original backend, into simpler ones.
Yeah, I think, I mean, I do think that one of the things that we'll be running into is that, there are some things that people are starting to do that are not just coming from the push forward and pullback operators. But I think that differentiation interface is probably the one package that can incorporate all of the weird extra little things that I see going on in enzyme specifically for Jacobians and such. So yeah, I think that there's everyone should learn. Everyone should go see that talk. Everyone should know what your what your Jacobian vector products are and your vector transpose Jacobian products are and everything. And but there's also a huge world, right? Anytime that we're talking about automatic differentiation, we'll say that, oh, it's making it simple, but there's always like a whole lot of layers of complexity, which is kind of being pushed to the side a little bit, that we want to kind of that is all about being automated. I think at this point, I think the differentiation interface is really doing a very good job at making it so that way you can get to this high level, you get fast enough code, but there's a whole lot going on under the scenes to be able to get there.
Yeah, but I want to put my foot down in the sense that differentiation interface is only useful because it remains simple, because it doesn't require people to read through the different documentations of everything. And so there will come a point where many people are using it and where many people will have different requests, sometimes contradictory, because they each want something for their own ecosystem. Like maybe the SciML people will want something, and maybe the Turing people will want something, and the Flux people will want something else. And at some point there will be, calls that have to be made on, do we keep the library simple and easily accessed, or do we satisfy every client request? And right now I'm strongly favoring the first option, which is to say, okay, differentiation interface may not be for literally everyone, but it should be enough for 99% of use cases. And then the 1% left over, then we'll see. But for instance, it's a deliberate choice to not incorporate any higher level operators. We only do first order derivatives and second order derivatives, because that's like 99% of actual applications. So anyone who needs third order derivatives, don't ask me, because you're advanced enough to figure it out yourself, essentially.
Yeah, I mean, those SciML people really ask for weird performance things, so there's
They
no
do.
reason
They're
to
the
ever listen
worst.
to them.
Honestly,
Yeah.
SciML the
SciML
worst.
people, yeah. So, but I needed a second to reflect on what I just heard, because I now in my mind cannot really square the two things that you mentioned. That on one hand you're only forwarding the computations to the backends and only putting in stopgaps if the simple building blocks aren't there in one particular package. But you also said in the previous answer that what differentiation interface.jl, I'm having difficulty with this name, is doing a lot of pre-compute. So where like, does the pre-compute needs to be adapted to every single backend package, or
Yes. Yes. Definitely. And that's part of the beauty of it, is that before, if you wanted to get optimal performance for forward diff, you'd have to go into the forward diff documentation and figure out, oh wait, I need to pre-allocate this object called a config, and it automatically checks the right chunk size, and it pre-allocates the buffers for the gradient, etc., etc. And if you wanted to get optimal performance for reverse diff, then you would have to go to the documentation and figure out, oh wait, what I need is to pre-compute the tape and maybe compile it, but it may not work if my tape is value dependent in its branching behavior. And if you want optimal performance for yet another backend, you would have to go into the documentation and figure out, okay, what do I need to do before I run the actual differentiation? So the big benefit of differentiation interface is that we read these documentations for you, or the lack of documentation in some cases, and we figure it
reverse
out
diff
for
definitely
each
was missing a
backend.
lot.
For each backend, we figured out, okay, what is the optimal way to prepare the differentiation operation? And sometimes it's built into that package, most of the times, and otherwise we do nothing, because we can't do more than what the package offers. But yeah, that's the point, is that many backends offer many different ways to prepare for an operation, and we abstract them all away under a common name so that users don't have to worry about the internals.
So there is a list of for each backend, there is a list of best practices that you just need to follow, and the IJL
Just doing
package
a lot of lifting
is
there, yeah.
yeah.
Yeah, exactly.
It's just collecting these best practices before execution starts. Okay,
Yeah.
I see. And you already touched upon this with the modern Julia workflow, but tell me again. So at what point did the IJL, if I may call it this, because otherwise I will never get the
You are
pronunciation
allowed.
easy. uh, so at what point did this momentum from, okay, we're developing the modern Julia workflow, to, yeah, okay, we now focus on, I guess, or are you focusing actually on the IJL package?
Yeah,
At
I'm
this point?
definitely giving it a lot of time. And I guess it sort of shifted naturally. We got it off the ground as a sort of prototype, and then we figured out, why did abstract differentiation not get traction? Because it was not fast enough. And so we started listing all of the issues that were still open on the abstract differentiation repository that never got closed because they never got fixed. And I just so you know, I didn't start by burning it all to the ground. Like I
Mm-hmm.
used abstract differentiation, I contributed to it, I maintained it for a little while, so I knew its ins and outs. And at some point, I recognized that it would take a very breaking and essentially transformative rewrite to get it to where it needed to be. So we thought it would be easier to start our own packages and sort of do it ourselves. And then maybe we would merge, but maybe not. And it ended up not being merged. And actually, it took off. So right now, it's being used in a part of the SciML ecosystem in nonlinear solving, in optimization. It's also being used indirectly in Turing, for instance. So it's starting to get really popular in a lot of places. I think because we made the design choices that were inspired by abstract diff while fixing the few remaining issues. We started getting deeper into it, we actually realized, wait, it's going to take more than just autodiff. It's going to take sparse autodiff to really go where we need to be. And then we open a whole new can of worms because there was an existing ecosystem around it, which was called sparse diff tools, but it was very specialized to two different packages, right? And it essentially had implementations for two packages, mostly forward mode, only Jacobians. And to go from there to the level of generality that was needed, we had to rethink everything from scratch. And we had to do a new package for sparsity detection, a new package for coloring algorithms. And all of this is basically taking ideas that were present in the literature on automatic differentiation 20 years ago and bringing them in a renewed form to the Julia language. The Sparsity tool was a first effort, and it was really great because, I mean, obviously it's used in SciML, so it has to work, right? But I think we took it to the next level by saying, okay, wait, you read these papers, but you actually missed a few things on like symmetric coloring of the Jacobians,
But we
or
ran out of
maybe
time.
faster sparsity detection. So yeah, we got much deeper into the rabbit hole than we thought we would, but it was really fun, and it's going to lead to a lot of, I think, amazing progress.
I 100% approve of it. Yeah, I mean, we ended up doing a lot of stuff in sparse diff duals specifically towards trying to get the sparse Jacobians required for because sparse Jacobians show up all the time in PDE solvers and such. So we went straight for that. And then, the GSOC projects and stuff were done. We're like, okay, we're good. And then people were like, oh, what about Hessians? Do you like optimization? We're like, do we need to? And so, yeah, I kind of sat there for about 2 or 3 years. And then you're like, oh, I want to start doing some sparse automatic differentiation. Why didn't you do these things? I'm like, have fun. And I think that you've had a lot of fun, right? I think that, the sparse connectivity tracer, I think, has been one of the major things, right? So, there's been this like arc of the sparsity handling pieces, right? So the beginning of the arc is the sparsity detection .jl, which is like where we introduced the sparsity programming kind of piece and everything. And it was a lot more ambitious, right? There are things inside of the algorithm there that you can't do with multiple dispatch because it has concolic fuzzing and things to be able to handle all sorts of edge cases with while loops and everything. And then we realized that maintaining that as a compiler plugin is just like way too much work. So then we built a different version just using symbolics.jl. But it turns out that the symbolic representation is able to do way too much. It does way more than you actually need for sparsity detection. Go check out the sparsity detection algorithm. It's actually very simple. You're basically just asking, do these things ever touch? And if they don't, then you have a 0 in your Jacobian. And so you don't need to actually know the whole symbolic representation of the equation to do that, right? And so I think that what you've done now with the sparse connectivity tracers, you've developed a very specific, optimized abstract interpretation algorithm that is just that algorithm of do these things touch. It has the limitations of the multiple dispatch form, right? So there could in the future be a lot more to be done there, but under those limitations, you got a very fast algorithm that works for like 99% of people's codes, which I think is a really strong contribution there. So yeah, I mean, so I would say that everyone should be checking out, Sparse Connectivity Tracer and take a look at it and how it works and everything. It's a fairly nice package, even though that's just one small part of the differentiation interface project, right? There's a lot of these little bits on top, but each little detail could be talked about in so fine a detail.
Yeah.
So
We should try to remember to put the link to Sparse Connectivity Tracer in the show notes.
Yeah,
Oh yeah,
and
we're
the
gonna
third
we're gonna
one,
be doing the
yourself.
thing now, right? Where we just say,
Yeah,
here's the link, right? And then yeah.
the third package in the Trinity is called sparse matrix coloring, and it's also revisiting what was called Colpack in C and C++. So
yeah.
it's the third package that enables sparse autodiff, and you should definitely also check it out. And we're writing
Yeah.
papers on each of those.
Cool. So, but the thing that still sort of amazes me on a, let's say, meta level is how much traction this the just the AD getting AD, well, not right, but making AD accessible to so many people in one place, if you will, was such a high need from the community, right? I mean, I guess, or my interpretation of what's going on is that Julia obviously caters a lot to very fast but very high level numerical computation, and so having AD is a super high need right now that has not been as conveniently, let's say, fulfilled
Packaged as in
as
Python. Yeah.
yeah. And
Yeah, so
so
the goal is really to convince people to switch to Julia by saying, okay, you don't actually need to know a lot to get fast code. That's
yeah,
really the point. Is we studied AD, we read the papers, we read the docs, and we implemented it for you. So just go ahead and give it a try and see how fast you can go by relying on pre-existing code instead of rewriting it from scratch.
yeah. Do you think there's, particularly maybe from your background from modern Julia workflow, do you think there's more sort of these undiscovered islands where users just not have the one most convenient package to solve that particular problem in Julia, so they stay with other technologies?
I think the next one I would want to tackle, because it's linked to my background and education, is graphs, because the graphs
Mm-hmm.
package is amazing, but many people have actually ended up implementing variants of it for their own specific needs with like vertex labeling or different storage mechanisms, etc. And essentially most of the graphs ecosystem was developed maybe 10 years ago. It was among the first big Julia projects, and it's already fast and generic, but I think with a little elbow grease, we can make it even better and start unlocking all of these GPU benefits, maybe, or sparse matrices in CUDA and stuff like that Ray has been working on at MIT. So I'm really excited to once we fixed 80 once and for all, because obviously that's what we're doing, move on to another chapter where we take another big chunk of the Julia ecosystem and ask, okay, there's this software that works well, but which we can improve. So how do we go about doing that? And in the process, how does this give rise to interesting computational research questions? Because of course I'm a researcher, so I'm evaluated on my ability to publish papers. But it turns out you can actually start from the needs that concrete people have, from like, oh, my code is running too slow. And then you end up finding research questions that are interesting in their own right.
Mm-hmm. Yeah. And the other thing maybe is that so the origin story of the DI.jl package was the modern Julia workflow and also your passion to teach. But the other aspect of this is in some sense you now solve the technical problem for people so they don't have to become the technical person themselves anymore, right? And my question is, like, do you have a feeling, and this will be a very vague and abstract question, so feel free to take it wherever you want to. How is this relationship where we need to get new users to Julia to be able to maybe, like, I would not have been able to write the DI.jl package, right? This is something that I need giants to stand upon. But at some point, we want everybody to be the giant for themselves, and we want to be a group of friendly giants, I guess.
Like in Roald Dahl's novel,
I
The Big
need
Friendly
to,
Giant or something. No?
yeah, I will need to read it.
Well,
So
there's also like what the song or show that's like "We Are Giants." Yeah, but sorry.
There's also
yeah,
that. No, but I understand what you mean. It's
yeah,
and I guess everyone should be or try to contribute in the area that they feel most comfortable in. And at first, I didn't know shit about autodiff, and the reason why I got into autodiff was actually because of Frames. Because Frames is one of the core contributors to the Julia ecosystem, and she in particular was responsible for the project called Chain Rules. And Chain Rules is not only a foundational part of the AD system, it has a wonderful documentation. And that's really what got me roped into this whole thing, is that Chain Rules was so amazingly documented that I felt like I could learn about AutoDiff. When I needed Chain Rules for one of my academic projects, I got into this and I thought, oh, AutoDiff is actually interesting. And then slowly I got more and more interested into it. And eventually I started contributing. So my goal here is to make it easy for people to onboard this thing, to start using it. And then if they're interested, they can actually check out the documentation for, let's say, differentiation interface, or maybe read the papers that we're about to write and get into it themselves if they want to. And if they don't, they can focus on what they're good at. So if they're neuroscientists, they can do neuroscience. If they're physicists, they can do physics. If they're chemists, they can go to hell. So it's really all about playing to your strengths. And if you decide that your strength is going to be AutoDiff, then it's amazing, because Julia allows you to be at the same time very high level and very high performance. So that's definitely something that you can do.
Is this particularly maybe the documentation part? Is this something where you would advise students to, if you want to get your feet wet a little bit, just see whether you can improve the documentation here and there, and then go from this? Or
that's always how it starts. The very first issue you open in any Julia repository is usually a documentation issue. There's like something you don't understand, and you maybe open a pull request to fix a typo.
Compiler.
Yeah, but most people start on the docs, and then you get nurse sniped. I remember one time I opened a documentation PR on benchmark tools, and then Valentin Chouravi made me maintainer so that I could merge my PR and take it off his hands. So I ended up maintaining benchmark tools for like a year just because I fixed a typo in the docs. I had no idea about metaprogramming, by the way. It was fun. So my point is, if you want to start contributing to the Julia ecosystem, the best way to do it is find some docs and try to improve it, because you think it will be worthwhile to beginners. Definitely, that's a good advice. And then once you start doing that, you think, oh, maybe to understand the docs, I should read the source code. And because it's Julia, you can actually read the source code without your eyes bleeding. And then once you read the source code, you're like, this is interesting. Maybe I should read the paper that described the source code. And from there, you go down into the rabbit hole and you end up building something new and amazing and shiny that will benefit people.
Or the other thing is you look at the source code and you go, why did they do this so slow, right? And then there you go. Now you're a maintainer.
Exactly.
That's cool. All right. So let's now circle back to the future plans, I think. So
well, I think I got one more question.
Yeah, sure.
Yeah, right. So a lot of times when you're developing a library, there's usually some kind of like a driving or grand challenge problem that you have in mind. I'm kind of curious, for differentiation interface, is there what is? Sorry, my cat is throwing his tail in front of the camera. For differentiation interface, what are your grand challenge problems? Like, what are the things that you're looking at in the ecosystem? You're saying, like, we know that we've done a good idea. If this is good, and this is good. Do you have those kinds of problems in your mind?
Yeah, we have a few sort of thermometers of how well we're doing. One of them is obviously adoption in SciML. So the whole ordinary diffie-q, nonlinear solve, etc. So that's obviously, because it's a huge selling point of Julia itself, we want our code to be used there. So a huge metric that we look at regularly is just how many SciML packages are thinking about adopting us. And what's really pleasant to see is the number of monthly downloads on differentiation interface is skyrocketing because of that. So it's really nice to see that we're close to, I think, 20K monthly downloads for a package that was created this year. So it's pretty amazing. But we have other parts of the ecosystem that we also want to attend to. Recently, I snuck differentiation interface into Turing, sort of through a back door, and now we'll see if they want to use more of it. We have this whole Julia Smooth Optimizers organization with nonlinear programming models that they are interested in solving, and for which they need sparse Jacobians and Hessians. So we have a lot of different ecosystems. I think the biggest ones, the biggest fish that we're going to need to fry is the deep learning ecosystem, because it's the one where the data structures are the most complicated. So that's kind of one step further, because most AutoDiff backends can handle arrays, but as soon as you go to nested dicts of tuples of structs, then it's a lot trickier. But that's where we want to go. But I don't really have sort of a big grand challenge, either practical or theoretical. I just want to get my code out there and see if it helps people. And it's obviously helping people, so we're continuing in that direction.
Yeah,
How
I find
does
that interesting because I mean, because you said that you're going to be doing a permanent position in transportation research,
Yeah.
but it sounds like you've now disconnected the work from the differentiation from the transportation stuff. Do you have do you have a transportation challenge that you're trying to solve with it as well, or it's
It's
like kind of been on a orthogonal kind of split?
it's been a bit orthogonal, but I think we might actually be circling back. Um, it's a bit of a struggle for me because I did a PhD that was motivated by industrial applications with the French railway company, but then COVID hit and I didn't interact with these colleagues from the train company as much as I would have liked, and so I ended up doing maybe more theoretical stuff and writing more algorithms and seeing less concrete data, and it I'm still struggling to figure out what kind of researcher I am now that I'm getting a permanent position. Maybe, and don't say it too loud, maybe I'm a bit more of a research software engineer. Um, and
Don't
maybe
worry,
that's
we'll
okay.
keep it on the down low.
Exactly. But the point is there's various ways to do interesting research with practical applications. And what really drives me, I figured out during these last few years, is the practical application. Like, okay, I can do theory if I want. I can read the papers. I can write some high level code on Autodiff. But the end result, the one that I actually care about, is people telling me, "You, I solved an ODE 10 times faster thanks to you," or I've solved my optimization problem on Power Grid management 1,000 times faster because of you. That's what I really care about. And so I hope that my future permanent position will allow me to start from concrete problems, like, okay, we need to handle this logistics system for a big company or even several, and we need to figure out how to reduce their carbon dioxide emissions by, let's say, pooling the truck routes or making smarter loading systems, or delaying the deliveries so that they can be mutualized, or things like that. And that requires optimization, that requires discrete optimization in this case. And so what I hope to be able to do is to take these really nitty-gritty concrete problems and then abstract them away by saying, hey, what we need under the hood to do this are fast graph algorithms and fast automatic differentiation, maybe to solve the continuous versions of these problems, or maybe a better integration into jump of certain solvers in the discrete optimization world, or maybe GPU support for graphs if we have really huge instances. And so you take this concrete problem and you say, what do I need in terms of theory and in terms of software to solve it well? And then you spend a few months working on that, and then you go back to your problem and say, okay, here's the solution. It uses that software, and it's 10 times faster than what you had before. So
yeah
that's what I hope to be able to do.
I one thing that really struck a chord with me in your answer here is this, we all are looking for this thanks to you moment, right? So this is, and you can achieve this in many ways. You can be a good research software engineer. You can be a good teacher, and then people will say, thanks to you. I mean, the modern Julia workflow
I mean,
is
isn't
an
that what we're all looking for? I mean, you can open a
Oh,
cash open and
definitely.
get that.
I'm a
yeah.
sucker for recognition. I admit it.
But
Like, guilty as charged.
I think this is why I am feeling so comfortable in the Julia community, because what I perceive at JuliaCons and on the onlines, on the webs and everywhere, is people are very good with giving recognition. So, for instance, at JuliaCon, you immediately also told Adrian, "Hey, come on stage with me, please." And today you mentioned Valentine and Frames and all the people. Also, this thing where we learn from mistakes and also say, okay, a subpar solution, let's say, is an opportunity for everybody to learn and to improve upon, right? So this optimization spirit is it's a friendly optimization if you want to.
Yeah, that's so the I think the most wholesome part of the Julia community is this channel on Slack called #appreciation. That's
Yeah.
really my favorite channel by far, because people randomly post, "Oh, I just love this package. It's so well documented," or "Oh, it made my life, 100 times easier because it allows me to do this and that." And it's just free nuggets of love and appreciation and recognition that people give each other in the community, and I find it really, really sweet. And you're
And
right.
also hashtag appreciate grapes, right?
Yeah,
If someone
because
gives you appreciation, but then they say you haven't done everything right yet, then you know it's genuine, you know?
yeah. So that's what I really like. And you're right. I'm like, one of my main drivers is feeling like my work is useful and that my work is appreciated. And of course, whenever I don't feel like that, I immediately, go rogue and start, bickering maybe on GitHub about how, everyone is a fool and they don't understand anything. But really, um, there's this sense in the Julia community that we're all building on top of each other's work. And it brings me to probably my most common dilemma in building differentiation interface, but also the graphs ecosystem and other projects is, do you go solo or do you build on what's already there? And it's a very difficult question because it's a technical question. Like, is what you're proposing different enough from the status quo that it's worth starting from scratch and possibly risking, a split or the fact that you're going to have fewer users? Is your project worth it? But at the same time, it's also a social question. Like,
Yeah.
are you in good terms with the people who develop the current state of the art? Do you want to help them? Do you want them to help you? Do you want to work together? Or do you want to work against each other? And what I really try to do with differentiation interface is work with everyone so that we can build this and all use it. But it required, in a way, starting from scratch and sort of archiving abstract differentiation, which was a difficult decision that we wondered
Oh,
about a
no, it
lot.
wasn't so difficult. I want you to
Well,
kill it.
no, but it was for me because I worked with
Yeah.
Mohammed and he also had a big hand in it, and I appreciate him a lot. And so it was a difficult decision, and it's going to be the same probably when I start focusing more maybe on graphs. Is okay. There's this huge, amazing ecosystem that exists already. Maybe it's due for an upgrade, and maybe we need to break everything to rebuild it from scratch. I don't know,
Yeah.
but it's always a difficult question, and the answer is always, if you want to build something new, reach out to the people who already did this before because they know about it already and they've probably gone through the same questions that you have. And so whenever possible, try working with them instead of against them. For instance, in the differentiation interface case, whenever people cite our work, we ask them to also cite abstract differentiation because it was the original inspiration. So in a way, it should also count towards their academic merit and so on. So that's really what I like about this community is we can all work together. Of course, there's like tensions; people don't get along, and that's fine. But whenever we can, we try to just keep a good spirit and progress together.
Yeah. That's cool. So I now can come back to the technical part. Is when you mentioned where the IJL might be useful, you did not mention Jump as a big ecosystem, and um, this is, as someone who was not as familiar with Jump, I always had this impression that okay, this is operations research community is very heavy on Jump. The more, let's say, driven by physics and chemistry people go to SciML for their compute needs. But now you seem to be sitting in the middle between both communities, right? You have this package that is very useful for everybody that does scientific computation, but you are actually coming from the operations research with the transportation. Um, uh, yeah, please take it from here. My English will break
Yeah,
down.
so it's a good point. So Jump is, of course, another huge selling point of Julia, and the work done by so many people in there is amazing, especially Oscar, who's a huge asset in terms of maintenance. I don't know if you know, but every time someone posts a question on Discourse about Jump, they get an answer from the man himself. Like Oscar always answers every single question to the best of his ability. So it's a huge project and it's working really well, and it actually predates most of the autodiff backends in Julia. So of course, to perform nonlinear optimization, Jump needs its own automatic differentiation system. But the difference is Jump actually has access most of the time to a more detailed representation of the function that they want to differentiate. Uh, what differentiation interface is doing is take a function that is expressed as a Julia function. And what Jump is doing in many situations is they have maybe I'm wrong about this, but essentially they have a sort of symbolic representation, or what could be presented as a symbolic differentiation system that takes a structured representation similar to an expression and then computes derivatives or gradients or Jacobians. And that's very different, right? And so that's why
Yeah.
differentiation interface cannot be necessarily useful to Jump, because they handle things in a different way, because they ask more from their users. They ask, okay, you need to specify your model with these macros so that we know what are the constraints, what are the objectives, what are the variables. But as a result, they have more information about the problem, and they can go about optimizing derivatives in a smarter way. And recently, we did some benchmarks on an optimal power flow problem with Adrian, and I got back to his long thread on discourse about benchmarking this problem with different optimization systems. And Jump is fundamentally different from NLP models and optimization.jl in that it doesn't work with Julia functions most of the time. It works with a bit more structured expressions. So it does a lot of pre-processing to sort of put this nicely into little boxes where it can do the differentiation. So it's really different. I hope that I might be able to contribute, but maybe not exactly in that way. One area where I'm looking forward to contributing, though, is this new package developed by François Paco, among other people, called Exa Models, which is basically Jump on the GPU. And that's really interesting because it relies on users specifying the problem in a way that has lots of redundancies, so that individual derivative evaluations can be parallelized. And it's kind of like sparse autodiff on steroids. And that's, I think, a really cool project. And maybe one of my research directions for the coming years would be to figure out, okay, how can we leverage this awesome power of GPUs to do more stuff with discrete optimization, where it's much less explored. And there's been some work in this area, but I think none in the Joy community. And Joy is especially well positioned to work on GPUs because we have an amazing ecosystem with people doing incredible things in kernel abstractions, which once again take off the burden of knowing what's inside the GPU to focus on writing the actual code. So yeah, Jump is a bit different, but there's still going to be connections, and obviously we can work together.
I think in 3 years actually. So if folks that don't know, if you really want to go do the nerdy thing, what you need to look into is what was called reverse diff sparse.jl, and then it was actually archived as a repo and moved around a little bit and stuff. But if you were to look for reverse diff sparse, you'll see that, right? So Jump has had this internal reverse mode automatic differentiation engine, which I think was written in 2015.
Yeah, so it's
And yeah,
basically a grandpa in terms of Julia packages.
yeah. But the interesting thing is that, yeah, because it acts on a symbolic interface, right? It's been able to do these optimizations that you can't really do in something like Zygote, because it needs to be able to do interprocedural optimizations on the level of the gradient, right? And the way that something like chain rules works is it kind of has all these dispatch rules, but you need to kind of not just do individual dispatch rules, but there's combination and fusion rules and such you need to do in order to get all of the performance out. And you need to do that sparse, which of course something like Zygote on its own doesn't do. But differentiation interface has a lot of sparsity handling things. I think it has more advanced coloring algorithms at this point than what's in reverse diff sparse and whatnot.
Possibly,
And
yeah.
for the interprocedural optimizations, in theory, you get them when you use enzyme with reactant. So while right now you cannot replicate that with everything that's out there in the ecosystem, I really do think that in like 2 years, like differentiation interface with enzyme with reverse mode should actually be able to do a replacement for reverse diff sparse. So that's my
Maybe. We'll
guess.
see. I think you're right about the coloring, especially because we designed a few new coloring algorithms of our own with Alexis Montoison. And so, spoiler alert, you're the first to hear this, but bidirectional coloring is dropping today. So from today, we might be able to compute Jacobians mixing forward and reverse mode in case you have a dense row and a dense column.
Yeah. Well, now you're just telling everyone how long it's going to take to put out this episode.
Yeah. And no, but you're right. The other very exciting thing in the ecosystem right now is this combination of enzyme and reactant, on which Billy, Valentine, and others are working a lot. And there's going to be sparse automatic differentiation in enzyme as well. So maybe it's going to be a full-on replacement for a differentiation interface. Maybe it's going to be complementary. But I'm sure excited to see where it leads, because you're right. We can do these sort of optimizations at the compiler level, which is not possible when you just have plain Julia code. So the problem, of course, remains that enzyme and reactant, no matter the documentation efforts, which are huge, they're still very advanced pieces of software, and they're not for use by everybody. Like
Yeah, I
it's
think even if it works, you still want to interface in front of enzyme for most people.
exactly, it's like a Ferrari. Like you may want to go at the speed of a Ferrari, but you don't necessarily want to take the risks of driving it yourself.
Yeah, and like a differentiation interface is like putting a bumper sticker on a Ferrari.
Yeah, or playing Gran Turismo instead of driving for real. I don't know, but that's the point, right? It's to make it accessible for everyone, and then that way people can get nerd sniped into giving a more shit about what's going on under the hood.
But I think it really highlights a thing about the ecosystem, this development stuff, and everything. Because like jump and its reverse if sparse is extremely good work, right? But once you start to centralize a lot of that work in a specific thing, we say, okay, now we have all the things going on for differentiation going on here, right? Then you can actually have the time and dedicate. Because sparse diff tools, we're able to do some things that we needed for Jacobians, but once you start to put it all in one place, then you can get more people to just work on, okay, let's finish out the sparsity here. Let's finish out all these coloring algorithms. Let's go the next step and everything. And sooner or later, it will do better than the things that are baked into a specific package, just because you've now generated a community around being able to use this in 100 packages. And so with more uses of it, then you just get more contributors and kind of have this successful growth of the community around it, right? And so I do think that there are a lot of bits, some within SciML, some within Jump, but which you're like, oh, this is going to be a very hard thing to get rid of because it's really built for this application, and it will be hard. But I do think that this community development has its own positive feedback loop that makes it so that way sooner or later, I think it's only like a year or two away from kind of being able to usurp a lot of those little internals, and everybody I think will be happy to be able to delete extra internals.
Yeah,
So,
what brings me a lot of joy is seeing these pull requests that adopt differentiation interface, and where the number of deleted lines far outweighs the number of added lines. Like the one
oh
in
yeah.
optimization base.jl, for instance, was pretty amazing in that regard.
Yeah, I mean, and optimization base was a great one because Vibe Hub and I had been implementing, have been maintaining, like 6 different differentiation interfaces for a few years, and so it's finally just like, yeah, we think differentiation interface is ready now, and we don't want to be maintaining like every little detail here either. Let's see how it works, and then we put the PR together, and so actually, okay, the enzyme case, there are some optimizations we still need to do there, but for the other 5, it's about the same performance. So delete a few thousand lines of code and just call a differentiation interface, and now we're good. Right? That's always the best PR because in an optimization library, we're planning to work on optimization, and we spend like 50% of the time working on differentiation stuff. You don't want to do that, right? So like this community organization is such a nice thing in the way that it evolves. And, it's just over time it just kind of builds out its own little pieces that can are reusable parts. And I think that is one of the things I've loved about Julia, just because like in something like PyTorch, right? You're building a machine learning library, you're also building the automatic differentiation library with it and all those little parts, and you just find that what you're actually trying to work on, you only spend like 10% of your day on, and you do 90% of your day on creating a new JIT compiler and an automatic differentiation interface, and it's nice to see these separations when they happen, because it just gives you this more reusable tools and more ways to be able to contribute to other people's work, even if you're not even if I'm not working on optimization all the time, right? If I'm doing something that does something in differentiation, then it affects libraries that I have never even heard of before, and it's just such a cool way for the community to self-organize.
Yeah,
Sorry, I
and
just had to
it's
go on to
very
like my happiness like of the Julia
no,
community part.
it makes me happy as well. It's this modularity that enables you to contribute, even though you may not be an expert, but you can contribute a small modular self a standalone package, and it gets reused by others. So some may call it the unreasonable effectiveness of multiple dispatch.
So one thing that always amazes me about these conversations, and I hope you out there, now breaking the fourth wall to the listeners, feel the same way, is that once we dive deep into these discussions with the experts, it's just so motivating.
Who's
So
the experts?
well,
Scary.
in this
Are they in the room with us?
Today it was you.
Oh, damn.
And you did like from playing the constant beginner, and I might ever hopefully maybe I'll reach, like, I'm looking up to you, and I think maybe many listeners will do as well. So now that we're all motivated, and now that we really want to, okay, let's contribute to the community, let's write pull requests. Do you have like concrete examples in mind where, okay, please, you wonderful people, newcomers, go look at the documentation of this package and add documentation, or maybe also Chris, I don't know, if you have examples of, oh, here's we know of this package that still has a lot of has a lot of handwritten DI rules, and find these packages where you can press delete and only import DI, and then this will be a cool pull request. Like, what should we be working on now?
I mean, I agree that it's a good project for beginners to find a library they're using, and then they can go look. Usually, starting in 1.9, Julia allows package extensions so that you can use functionality from a package without fully importing it and forcing the dependency. So if you're using a library that is somehow connected to gradients or differentiation or optimization or machine learning, you can check out in the extension folder or in the project.toml file if there's an extension or a weak dependency on an automatic differentiation backend. And usually, for most libraries, this is not needed. Like, if you see a different dependency on one specific optimization backend, there might be a reason. But if you see a weak dependency on two or more, then it's usually because they're trying to interface with several backends at once. And in all of these libraries, you can usually plug in differentiation interface at little to no cost. So regularly, I look up differentiation interface in the GitHub issues to figure out if people are wondering how to use it. But if you are using some libraries and you're computing gradients at some point, do check it out. Go to their project.toml, see their dependencies or weak dependencies, and if there's for diff or zygote or reverse diff or enzyme in there, ask yourself, do they really depend on that one choice of library, or could you abstract it away and let the user choose which autodiff backend they're going for? And that's a zero cost change most of the time.
And I think that one major contribution that a lot of people could do, which we really need inside of the differentiation experience right now, is full-fledged benchmark problems, right? We have the SIMO benchmarks infrastructure, so that way, if you give a a piece of code that you want to run, and you're like, oh, it takes like 6 hours to run this benchmark. Don't worry about it. You don't need to run it on your computer or anything. What we need is we need a lot more of these really real cases of like, okay, here I'm using differentiation in this real case. And if it's set up with differentiation interface, which is a good way to spend some time learning differentiation interface, right? If you have that problem set up to use differentiation interface, then differentiation interface has a lot of nice test utilities and such. We can help you update your code to use that. That will run through, 6, 7, 8 different differentiation backends, different choices of sparsity, and be able to just give a plot of here's how everything's working, right? Because I think that, one of the big things with automatic differentiation is there's still a lot of open questions as to where is the real cutoff between forward and reverse mode. It's library dependent. When is this library good, bad, et cetera, et cetera? And we just need to have, like 10 examples of just saying like, oh, here's a transportation problem. Here's a biological problem. Here's a, let's just have a whole ecosystem of these benchmarks. And if they're all maintained, then someone's question of which interface, what type of differentiation should I use, they'd be able to click on a problem that looks closest to theirs and see graphs of what the performance is like. So I think that we need a lot more people doing some differentiation benchmarks, because I know that right now we've thrown it onto you, right? You've done and maintained a few of them, right? And but we need a lot more of those problems out there.
Yeah, that would be amazing. So if you have a realistic optimization or machine learning problem where computing gradients or Hessians, especially with sparsity, is challenging, please, reach out and we'll help you figure it out. Because as of this moment, most benchmarks actually use this Brusselator example, which is very dear to Chris's heart, mostly because it's a wordplay, I think, because it's an oscillator from Brussels, as Adrian discovered, and so it's called Brusselator. but it's really like a
Okay.
standard example in SciML, and we're sick of it. So please give us more.
Yeah, I don't think everyone in the world is a mathematical biologist or a mathematical biologist by training who works on partial differential equations. So if you're not one of those people, or I mean, even if you are, we just need more example problems that just come from a whole lot of different disciplines. Otherwise, the only one that would be optimized is mathematical biologists, right, and chemists. Which I hear that there's very strong thoughts about chemistry.
So this might be a good point to okay, we're now really all motivated. Is there anything else, Guillaume, that you want people to take away that we have not touched yet?
If I had a magic wand and I could fix one thing about the Julia ecosystem, it would be interfaces. I think right now that's probably our biggest collective challenge. We've figured out a lot of stuff on like reducing compilation time, and there's lots of amazing things coming out in the 1.11, 1.12 releases. But the one thing we're still struggling with is defining and documenting exactly what we want our code to do, which is crucial if we want to keep building this modular ecosystem where we have individual small packages that talk to each other. And right now, it's made very complicated by the fact that we don't even have a strong notion of what is an array. What am I allowed to do with an array? Am I allowed to index it? Am I allowed to copy it? Am I allowed to blah, blah, blah? So there's, and it's the same problem for sets, for dictionaries, for a lot of different things, even for autodiff backends. Like some people mean different things when they say Jacobians, right? What if your input is a matrix? Do you output a Jacobian matrix or do you output a Jacobian tensor? Different backends make different choices. And for all of that, I think a programmatic way to specify interfaces and to check them would be very useful in terms of bringing the ecosystem together and bringing it to a higher level of maturity and robustness. So that's really, I think, the one challenge that we need to focus on as a collective. And there's been some, initiatives in this regard, a few packages that are third party, but it's one of those things where you need a standard built-in solution so that you don't end up like Python with 36 package managers, right? You need one thing that's in the core language, and that's that. So yeah,
Yeah.
that would be my wish list.
Yeah, I think that if folks haven't seen it yet, I don't know how much press it got. There is a talk by Jeff Benson on part of the HEP Foundation, right, High Energy Physics Foundation, on Julia for C++ programmers, where he goes into a lot of detail on the oncoming developments in terms of compilation interfaces and other like compiler level features. So I'd say go check out that talk from the Julia HEP group that he recently gave on for some of
Thank you,
that,
Michael.
because yeah, there's a lot that needs to be done there, and we definitely need to have a way to be able to tell everyone, like, the proper way to define a gradient is that a gradient's a row vector, right? And we need to be able to tell everyone that this is how it's done. So
This would be the worst.
there are some hills that I won't necessarily die on, but I'll keep mentioning.
All right. So I think what we've achieved today is we've learned a lot about differentiation and how
to pronounce my name.
Well, it's an hour ago we knew how to do that, but
I'll have to relearn it constantly. But that's a me problem. That's definitely a me problem. I apologize, but I think everyone is now even more motivated to contribute. The newcomers have a way to start. The experienced Julia developers have a clear call to action to fix interfacing and defining this. And all that is left for today, I think, is thank you, Guillaume Dalle.
Wow. Yes.
I can learn. Okay, so thank you again a lot for being on the show. It was huge fun to talk to you and learn more about you and the stuff that you did. Thank you to all the giants that we're standing on today. So Adrian and Valentin, and there's many more names that I should have written down. And I hope everybody should be seen.
Shout out to Frames especially. Like
Yes.
She's the one who got me into autodiff.
Yeah.
Frames and Billy, and yeah, the list could keep going.
Yeah, and thank you all at home on your devices to listening to us, and thank you, Chris, and yeah,
and thank you, Michael. It was a huge. It was fun talking to you guys, and I wanted to come back when you said you look up to me. I'm moved, but the truth is that we in this community we look up to each other. Like I think what
Yeah.
you're doing with this podcast is amazing. I think what Chris is doing with SciML is epic. And so what I really like about it is that we can, each be good at our own thing without, throwing shade on each other. So that's why I keep coming back to the Julia community and building projects with people. It's because they're respectful and fun and kind and also super clever.
Well, I like that I like that you say that as you literally have this shade thrown on you right now because you have this Rembrandt lighting that most of your face is. So
That's an aesthetic
I like
choice.
the contrast there.
I see the light. I see the light.
Awesome. Thank you, guys.
So, see you guys next episode.
Bye.
Thank you. Bye.